This is a presentation I gave at Machine Learning Summit in Beijing in October 2023. The title of the presentation is Retrieval Augmented Generation, Current State and Challenges. So in this presentation, I'm going to give a brief overview of large language models, and then I'm going to focus on retrieval augmented generation. So my name is Jay, and I'm a former lead data scientist at Snap, and used to work as director of data science at Kuaishou, which is a local competitor of TikTok in the Chinese local market. So Kuaishou is also a short form video platform. My LinkedIn can be found in the through the following link. Feel free to add me on my LinkedIn. Before we officially start, let's look at this cartoon about ChatGPT. So the cartoon is about a conversation in a conference room. The female boss was asking her team member, what will be the impact of ChatGPT on our business? There's a lot we don't know for sure, actually. Like how much of it is made up, or if you take away of jobs, or the security risk of generative AI, or if it's going to damage the reputation of our company. Then the female leader asked, what do we know for sure then? The answer was only that we want to adopt it everywhere as fast as we can. This is a bit sarcastic, but it reflected how much the buzz was throughout the first half of 2023 in the entire internet community and also in the entire tech community on ChatGPT and the associated large language models. Numerous companies are building foundational models, building the infrastructure for large language models, building vertical large language models, and also applications on top of generative AI. In the recent few months, like in the second half of 2023, the trend is slightly cooling down, but still there's a strong passion for large language models and ChatGPT. So first, what is a large language model? I'm taking the definition by Google Cloud and made a slight modification of it. So in my definition, there are 4 keywords. The first keyword is large. So large is in terms of the computation in training the model, the size of the training data, as well as the number of parameters in the model. There is a scaling law being introduced by OpenAI and Google team. So it is a empirical law when people are fitting larger and larger natural language processing models. The simple version of scaling law has 2 messages. The first message is performance increases as computation, data size, and parameter increase. In layman's terms, the model performs better if the model is larger. These 3 factors need to increase proportionally for optimal performance. So this is a scaling law of large language models. The second keyword is general purpose. In traditional natural language processing, we build task-specific models for any task, like machine translation, like summarization. We need to build a specific model for this task. In the era of large language models, we can use the same framework. We can use zero shot, few shot, and through a similar mechanism to perform these tasks. The next keyword is pre-trained. This is about the current pre-training and fine-tuning framework. The base model are pre-trained with a certain objective. For example, the BERT model is aiming at mask language prediction as well as next sentence prediction. So it punches holes in the paragraphs of the training data and try to predict what is being masked. Also, it does next sentence prediction from the preceding sentence. It tries to predict what will be the next sentence. Similarly, in ChatGPT, the pre-training is in terms of next word prediction. We're trying to predict what's going to be the next word in a sentence. And in the fine-tuning of ChatGPT, we use RLHF, the reinforcement learning through human feedback. We also do instruction fine-tuning. The last keyword is emergent abilities. There is a seminal paper by Google called Emergent Abilities of Large Language Models. So I'm taking 3 emergent abilities here. For any interested readers, you can take a look at the entire paper for more details. The 3 emergent abilities include the ICL, in context learning. So for those of you who have used GPT or its similar variants, so you are familiar with the concept of zero-shot and few-shot learning. The second emergent ability is instruction following. So the base pre-trained model doesn't have instruction following abilities. For example, in GPT-3, we do fine-tuning with thousands of instructions. So we are teaching GPT how to perform tasks through instruction fine-tuning. What is surprising is even though we only showed it how to perform those around thousands of tasks, it has the ability to generalize to new tasks. So you don't need to teach it a task every time. The last emergent ability is reasoning. So for those of you who are familiar chain of thought reasoning, you are probably familiar with this emergent ability. There's a recent paper called Challenges and Applications of Large Language Models. So in this paper, it summarizes the 16 large language model challenges. For example, unfathomable data, which includes data leakage, data redundancy in the training set, and PII leakage, the personal identifier leakage. There are also other challenges like a high inference cost, evaluation brittleness, etc., etc. So among those 16 challenges, 2 challenges, including hallucination and a still challenge, still knowledge, as well as a lack of domain expertise. So these 2 challenges, they can be both mitigated by what we call retrieval augmented generation. So now let's take a look at what we mean by hallucination. There are intrinsic hallucination and extrinsic hallucination. Intrinsic hallucination means the generation contradicts with the source. For example, if we know the stock price of Microsoft yesterday was $300 US, and today is $330 US, we know the increase is 10%. But if you claim Microsoft stock price has decreased, then this is the issue with information. The second is extrinsic hallucination, which means we cannot verify the generation correctness from the source. Take the previous example. If we only know the stock price change of Microsoft, we don't know the overall market. But if you claim Microsoft has outperformed the overall market, then it is an issue with extrinsic hallucination. Because based on the existing information, we cannot compare Microsoft with the overall market. Now let's take a look at how we can get the most out of large language models. We have four options here. The first option is prompt engineering. Here we purely rely on the knowledge instilled in large language models. And as a large language model was trained up to a certain time point, it doesn't possess the up-to-date knowledge. For example, GPT-4 doesn't possess any knowledge after September 2021, and anything that happened after September 2021 is not known by GPT-4. The second approach is retrieval augmented generation. So here we combine retriever with large language model. In retriever, we can search the public internet, domain specific knowledge, and also companies' private data. And we take the retrieved results and formulate a prompt from the retrieved content. The next approach is what we call supervised fine-tuning. So a lot of existing cloud services already allow the user to fine-tune a model with users' specific data set. For example, in Microsoft Azure, the user can upload their own content and fine-tune the existing GPT models. There are two caveats with SFT, however. The first is SFT objective may differ from the pre-training. We can take ChatGPT as an example. In training GPT model, we use a next word prediction as the objective. However, in supervised fine-tuning, we use human feedback and use reinforcement learning from human feedback. And also, we did a lot of instruction fine-tuning. This is different from when we pre-train the model to predict the next word. The second is fine-tuning may overfit. The fine-tuning dataset is typically way smaller than the dataset used to train the model. For example, we may take a dataset of a few thousand articles, and we want to fine-tune the model with this smaller dataset. In this case, we need to increase the learning rate, but we need to be super careful as if you increase the learning rate too much, you may fine-tune, you may overfit through the fine-tuning. The last approach is, of course, to train the large language model from scratch. This is super costly. It may cost millions or even tens of millions of dollars to train a model from scratch. And you also need to have a strong expertise in deep learning architecture. Now let's look at the pros and cons of retrieval augmentation. So I have listed the pros on the left-hand side and the cons on the right-hand side. So the retrieval augmentation, we can retrieve with natural language, and it is scalable to billion scale records if we do approximate nearest neighbor search. So with RAG, we can manage data just like in the traditional database. And as I have mentioned previously, it can be used to alleviate hallucinations. Now let's look at the cons of retrieval augmentation. So depending on the quality of retrieval, we may receive no empty results from the retriever, or in the retrieval stage, we need to do some clarification to figure out what the user is really looking for. And the retrieved results may contain some errors, maybe some factual mistakes. So we need to be super careful with retriever and also with generating based on the retrieved results. Now let's look at the high-level architecture of retrieval augmentation. So on this page, I'm listing the 4 modules of retrieval augmentation. So the first one is document chunking. This is to create chunks of the document so that the chunks can be used as basic elements of our retrieval. The second is embedding. So from the document chunks, we can use some embedding model and get the embedding of those chunks. And we can save the data into a vector database. The third stage or the third module is a large language model. The large language model interacts with the end user, and it also interacts with the vector database to do the retrieval and to take the retrieve results and to generate the user response. So what I want to call out with the large language model generation part is it is often generation with evaluation. So it is a closed loop where we do the generation and then we do evaluation to check whether the generated results satisfy our requirement. We only output if it satisfies our requirement, and otherwise we are gonna go back to generation or use a different prompt to generate. In terms of retrieval, there are different modes of retrieval we can use. We can use a key value based retriever, or we can use a vector database. In the narrow sense, when people are talking about retrieval augmentation, people are talking about using the vector database as a retriever. For companies with their own knowledge base, they can use knowledge base in the retrieval stage. Now let's look at a few scenarios. So I'm listing 3 scenarios here. The first is personalized email response. In this scenario, when we want to generate an email response to a user in a personalized way, we could use a key value retriever. And from the user ID, we can get what we know about the user. For example, the user's age and gender, and also the user's interest. Through this information, we can create a personalized message to the user to increase the user response and satisfaction. The second scenario is few-shot learning. So the few-shot learning scenario we have already touched on previously. In few-shot learning, instead of presenting the user, presenting the large language model with no examples, we can draw some examples from our golden data and present those examples to the user. So the literature has shown that few-shot learning outperforms zero-shot learning in majority of the cases. And in few-shot learning, if we use examples similar to the task, it also will improve over the randomly taken examples. If we are trying to tag some financial articles in few-shot learning, we can start with some retrieval and find some articles similar to the financial article we are trying to tag. And this is going to improve the tagging by the large language model. So the last scenario is a chatbot with internal knowledge. A lot of companies are building chatbot applications using their own internal data repo. So this is a typical application of retrieval augmented generation. I'm sure a lot of you are familiar or are already building such applications. So I will not spend much time talking about this scenario. Now let's look at a retrieval augmented system called Atlas. which was introduced by Facebook back in 2022. So the Atlas system, during the pre-training stage, they used a masked language model. An example here is Bermuda Triangle is in the mask of the Atlantic Ocean. The word western part has been intentionally masked in the sentence. And in the pre-training, we are training the model to predict the masked words or characters. The Atlas is trained to perform a number of different tasks. For example, fact-checking. A statement here is Bermuda Triangle is in the western part of the Himalayas. We want to check whether this is a true statement or a false statement. Another task is question answering. An example question here is where is Bermuda Triangle? A correct answer to the question is Bermuda Triangle is in the western part of the North Atlantic Ocean. So in the Atlas system, the authors use the contriever as a retriever and use the T5 model in generation. So the authors claim that the system achieved an overall 42% accuracy on natural questions with only 64 examples. And this system outperformed the much bigger model with 540 billion parameters by 3%. Even though the model is 50x smaller. The paper also talked about retraining the retrievers. Instead of taking the retriever from off the shelf, we can retrain our retrievers. There are a few options in retraining the retrievers. One would be to do a full index update. In the embedding-based retrieval, the retrieval results heavily depend on the embedding model. So if we want to improve the retrieved results, a natural approach would be to update the embedding of the entire index. But this can be pretty costly. So a more cost-effective approach is to take the retrieve results from the existing retriever, but use a ranking model to rerun these results to improve the top K relevance. So this is a re-ranking approach. And the last approach is to do fine-tuning on the query side. Similar to the two-tower model in recommender systems, we can have a query and document two-tower model. So in this model, if we do fine-tuning on the query side, so the query embedding will be different. And thus, the same query will lead to different retrieve results given this updating. So previously we talked about the 4 different modules of retrieval augmentation. Natural list of challenges would be how you do each module. For example, how do you chunk the documents? How to choose the embedding model? How to guarantee the relevance of the retrieval? And how do you guarantee the quality of generation? So this is a modular approach, basically how you can optimize each module. But if you consider the retrieval augmentation system as a whole and consider the end-to-end performance, then the question is always how do you optimize the system end-to-end? Now let's look at the first module, which is document chunking. In document chunking, there are a number of factors to consider. For example, what's the embedding context window? So the context window depends on the generation model. If the generation model can only take 1K, 1,000 tokens in the context, then the document chunks should be no more than 1K tokens. The second factor is semantic. So in the document chunks we produce, we want to guarantee semantic coherence. So we don't want to break the same sentence or the same semantic flow into different chunks. Next factor is the natural structure of the article. So we can consider the natural structure of the article, and we can use some graphical representation, either use graphs or use trees to represent structure of the article, and then we can do some splitting based on the article structure. The last factor to consider is E2E optimization. So if we create chunks which are very coarse in granularity, meaning each document chunk contains not only what we are looking for, but also some unused information. Then it will introduce more noise in the retrieve results. But if you divide the document into fine granular chunks, each chunk will have the accurate information, but if during the retrieval we cannot retrieve all the relevant chunks, then we may have the partial information. So in this way, it's gonna be hard to do inference or reasoning based on the complete picture. There are a number of tools which can do document chunking automatically. For example, NLTK, LangChain, etc. So previously, when we talk about the factors to consider, we alluding to different chunking strategies. We can use a fixed size chunking, or we can do a content-aware chunking. So there are a few parameters in the chunking packages. For example, what's the size of the chunk, and what's the method of doing the chunking. So after chunking, assume we can create document chunks. The next question would be, how do you choose the embedding? How you generate embedding from those document chunks? For people who are familiar with search retrieval, you must be familiar with different embedding models. The sparse embedding, like the bag of words, TF-IDF, and the dense embedding. Starting from word2vec, the 2013 seminal paper on word2vec, all the way to the most recent GPT and BERT embeddings. There are a number of benchmark datasets to compare the embedding models. So there is a Beir, BEIR, MTab, and Qt. I mean, those are different versions of benchmark data. In building benchmark data, you should always consider building your own benchmark. For example, in the scenario you are considering, you are only interested in the cancer data set. Then what you can do is you can build your own benchmark data and then evaluate different embedding models based on your own cancer benchmark data. The next challenge we consider is retrieval relevance. So in talking about retrieval relevance, I'm taking some research results produced back in 2021, and the results were based on a benchmark data called Bayer. So the Bayer dataset is a standard test data, which consists of 18 public datasets. So essentially, we want the model to work on 18 different tasks. So all these retrievers were compared under zero-shot evaluation, meaning we don't provide any examples. There's a long list of candidate retrievers being compared, including a lexical retriever, sparse and dense retriever, retrievers that include late interaction, and also retrievers that included re-ranking. On the right-hand side, I'm showing the results of comparing different retrievers. The baseline here is BM25. Even though it's a simple baseline, but if you compare BM25 with the other more complex retrievers, it doesn't lose completely. So on the right-hand side, each column or each bar represents each retrieval model, and the green bar meaning the retriever under comparison outperforms BM25, and the red bar means it is losing to BM25. So if we take BM25 as a baseline, only two retrievers outperform the baseline on more than half of the results. The first approach is BM25 plus re-ranking, and the second approach is DocT5 query. So the first approach is BM25 with some re-ranking model, and in the second retriever, what they did is a document expansion. So they use T5 as a generative model, going from a document to the generated query for this document. And then we have an appended or expanded document with both the original doc and the generated query. Based on the expanded document, we can do lexical retrieval. So only these two approaches outperforms BM25 baseline. A natural question here is, should you train your own retriever? So if we go back to the cancer dataset example, so my argument would be in three steps. So in the first step, what you can do is you can use your own benchmark data and compare the different off-the-shelf retrievers, and then pick the best off-the-shelf retriever to be used in your application. So this would be the first stage. The second stage is we can integrate the off-the-shelf retriever with re-ranking. Suppose we have our own private embedding model, or we have additional features, then we can build a re-ranking model that re-ranks the retrieved results to improve the relevance. And the last stage, you can consider training your own retriever. So we have talked about document chunking and also retrieval. Now is the generation stage. So for large language models, we are all familiar with this saying. Basically, you can prototype an application in an hour, yeah, but if you want to ship it to production, it usually takes weeks or even months. So in generation quality, I'm listing three different ideas. The first one is self-consistency. So the key idea of self-consistency is we can generate multiple independent outputs from the same prompt. So we can compare the consistency among those different outputs. So if those outputs are similar to each other or consistent with each other, then we can infer the output has a higher confidence. Otherwise, we can conclude that the output has a low confidence. The issue with this self-consistency approach is pretty obvious. It could be true that all those different outputs are super consistent with each other, but they could all be wrong. The second approach is reasoning reflection. So in reasoning reflection, we ask a GPT model to do some reflection to see whether GPT or the large language model is confident of its output. So this will associate some level of competence with the output result. The last approach is introduced by Facebook in September 2023. It's called chain of verification, or COVI. So the idea of COVI is we can start by having some baseline response, and we can generate some verifying questions. Then we answer those verifying questions independently, and ultimately we find the results that are consistent with the verified results. This is a little abstract, but let's look at a concrete example. So in this example, we want to name some politicians who are born in New York. So the initial response includes the following three politicians. The first one is Hillary Clinton. The second is Donald Trump. And the last is Michael Bloomberg. Then from this baseline response, we can generate some verifying questions. For example, where was Hillary Clinton born? Where was Donald Trump and Michael Bloomberg born? Then we can answer those questions. So Hillary was born in Chicago. Donald Trump was born in Queens, New York City, and Michael Bloomberg was born in Boston. So the answers of the verifying questions essentially can allow us to do some filtering, and now we have Donald Trump left. So after talking about the generation quality, now let's look at the auto evaluation and measurement. So previously, when I was talking about generation, I mentioned the idea of having a closed loop between generation and evaluation. So I want to make some comments here. The first is we want to use both the large language model and rules as a judge. It is a pretty popular idea that we can use a large language model as a judge. But in a real world example, especially in applications like finance or medical literature, basically the tolerance for errors is very low. Like you can, in most cases, this is true or false. You cannot make mistakes. So with the randomness or stochasticity of large language models, we cannot rely on large language models as judge 100%. The second comment I'm going to make is large language model can be used to simulate independent judges. So in one prompt, we can ask a large language model to simulate multiple independent judges, and we can ensemble the judgment results from these independent judges. The other factor I want to talk about is how we can construct our own measurement. It consists of the following 5 steps. So the first is how can you generate, first is to generate your grounding data. And the second is to construct your own measurement data set. And then we can use the large language model to do the generation, and we can extract claims from large language model. Then we can verify the large language model claims with the grounding data, and then we use that to compute metrics. Now let's look at the asthma example on the right-hand side. In this example, we are using color blue. Now let's look at a concrete 现在开始。 Now let's look at the concrete example on the right-hand side. So this is an example conversation with a AI bot about asthma. So in this example, we use a blue box to represent a human question. We use an orange box to represent machine reply, and the grounding data is inside the curly bracket. So first, the human question is about asthma, and the user wants to um, learn about asthma. Hmm. Now let's look at a concrete example. So this is an example on asthma. In this example, we put a human question in the blue box and machine reply in the orange box. We put the grounding data in the curly bracket. So first, the question from the user is about asthma, and the user wants to know more about asthma. Here is a machine reply. The symptoms of asthma are recurring and reversible. The claims from this machine reply include, for one thing, the symptoms are recurring, and for another, the symptoms are reversible. Now let's compare those claims with the grounding data. In the grounding data, it did mention the symptoms are recurring, but on the other hand, it mentioned about reversible airflow obstruction. So reversible, this is to describe the airflow obstruction. It's not saying the symptoms of asthma are reversible. So there is a contradiction between the GPT or the AI claims versus the grounding data. Now let's look at what are the options for metrics. Generally speaking, there are two categories of metrics. So one is statistical metric. In statistical metric, we are comparing the output with the source, and we can compute some statistics based on a word match or an n-gram match. The statistics-based approach, it doesn't consider the semantic meaning between the model output and the response and the source. It could be possible that the model output contains the same semantic meaning as the source, but just because they use different phrasing, the statistical metric leads to low results. Now it comes to the model-based metric. So I'm introducing the natural language inference-based metric called QGQA, which was introduced back in 2021. Now let's look at how QGQA works. So in the conversation in the middle, I'm using the orange box to represent machine answer. So the machine output is saying coffee is very acid. It has stimulating effects on humans. So from this machine output, we can use question generation to generate questions. So the question here is, what is very acid? And a answer consistent with the claim is coffee is very acid. Also, we can use QA, question answering, with grounding data. So the grounding data is saying coffee is slightly acid and has stimulating effects on humans. The question we use is from QG, basically what is very acid? Because grounding data says coffee is only slightly acid. So the QA answer is going to be no answer. So now the QG answer is coffee, while the QA answer is no answer. So there's a contradiction between the QG versus the QA results. Another metric I'm introducing here is the fact score, which was introduced in October 2023. So the paper of fact score has three contributions. The first is it is information atomics. So instead of looking at the entire generation and ask ourselves, is a generation stating the facts or not? We break the generation into atomic information. For each atomic information, we try to decide whether this is true or false. The second contribution of the paper is it introduces a fact data set, and the last contribution is it introduces a large language model as a judger. So even though it is this idea is introduced in this paper, but in practice, in a lot of the AIGC systems, people have been using large language model as a judger. In this slide, I'll briefly talk about generation model, and it is a pretty light slide. So the first claim is the large-scale, more complex models usually have better grounding ability, which is pretty intuitive. So both in terms of generation and in terms of quality checking, GPT-4 model should outperform the GPT 3.5 model. During the generation, we can do parameter tuning to control the stochasticity. For example, we can tune the model temperature and top P in the model parameters. So model temperature can be used to control the stochasticity. A low temperature means low stochasticity, and a high temperature means a high stochasticity. In generation, we can use reinforcement learning from human feedback to align the generation with our expectation. And given proprietary data, we can always do fine tuning of the large language models. Okay, so this is the final slide. What is the take-home message of this presentation? So first, there's a simple equation. Retrieval augmentation equals to retrieval plus the generative AI. It's a pretty simple and straightforward equation. Retrieval augmentation can be used to reduce hallucination. We can also leverage private and the vertical domain data with low cost through retrieval augmentation. But still, it has a lot of challenges. It has challenges in embedding, in document chunking, in generation, etc. And as I have stated previously, the E2E optimization remains an open question. The good news is there is a plethora of off-the-shelf retrieval augmentation tools. For example, LangChain, Pinecone, Llama Index, etc. And those tools make it super easy or low code to build your own retrieval augmentation systems. So I'm going to conclude this presentation by the following image, which was taken in Beijing last year, when in last winter, because you can see I was still wearing a thick coat. So it's a picture between myself and a panther sculpture. So I was staring at this panther sculpture, and in the meantime, it was staring at me. So this resembles our relationship. I mean, the human relationship with AI. This conveys a pretty complex motions. So first, we are excited. We're excited about its capabilities. We also have fears. Um, we are afraid of the downsides it brings, from losing jobs all the way to the extinction of mankind. But we are curious. We're curious about what it can do for us, what it can do in the future. And also, as the AGI is becoming smarter and smarter, we have an issue with the incomprehension. We fail to understand the output it generates, and this will lead to confusions and incomprehension. All right, this is all about the presentation. Thank you very much for listening.